This is the Nanophotonics course, and here is the vital information. My name is Jang Min-seok, and you can see my email address here and my physical address. Oh, by the way, can you see my mouse pointer here? Or okay, you can see. Good. So when you email me, please include EE647 in the subject line so that I can immediately notice that your email is about the course. Otherwise, because I'm getting like many emails a day, so without this, it is highly likely that your email will just get ignored. Okay. And here are the teaching assistants. We have two teaching assistants. One is Han Sang-jun, and the other is Shin Jung-min. Both of those are actually now, in this virtual classroom. And if you have a general question about the course, you can always email these people. Okay, these are the email addresses. And of course, you can download the lecture material from the course webpage here. Here's the link to the course webpage, or I'll upload the duplicated information to the KLMS website, so you can download from anywhere you want. And another thing I'm gonna do is I'll try to record this Zoom session and upload it to the KLMS so that you can stream the video. So if you miss anything, you can probably replay the recorded video. Okay, so the time is Monday and Wednesday from 1 o'clock to 2:15. So what are we gonna learn in this class? We are going to learn basically these four topics. So one is photonic crystal and plasmonics and metamaterials and metasurfaces. Okay, and if you look at this plot, I actually created this plot last Friday. So I searched for the Web of Science website with these four keywords and count how many publications, how many papers got published per each year with these keywords. Okay, so you can see the publication counts. All these topics are actually increases rapidly, and except for photonic crystal. So photonic crystal is a little bit early topic. You can see it starts to gain some popularity at around like 1995, and then it gets already extremely popular in early 2000, and now it's a bit saturated because it's kind of matured field. And then the other three is relatively new. Plasmonics and metamaterials starts to appear around like 2003, 2004, and now these two topics are still increasing, but you can see the slope is a bit, flattened. We'll see what's gonna happen in a few days. And metasurface is the most recent topic, which is the metasurface is nothing but a two-dimensional version of a metamaterial. But because this is much easier to create, it gains a lot of popularity in recent years. And you can see here around like 2012, 2013, it starts to get starts to become popular, and now it's rapidly increasing field. So the reason why I bring this chart is because I just wanted to stress that the field of nanophotonics is rapidly growing, so it's worth learning. And I understand that many of you have different backgrounds and just wonder, if this was an offline class, I would ask why you are taking this class. so that I just kind of gather your interest and then probably change the lecture topics a little bit in order to adjust your interest. So if you want to learn any specific topic in the field of nanophotonics, it'll be better just to email me or just tell here so that I can reflect your interest to organize the lectures. Okay. So do you have anything you want to learn except for these, like plasmonics and photonic crystals and metamaterials and metasurfaces? If you have anything, you can type it into the chat room, or yeah, well, prefer to. Yes, photonic crystal will be covered. I mean, these four, of course, will be covered, but except for these four, if you have anything additional you want to learn. Okay, well, if you come up with anything, just let me know. So what I'm going to do today is to just give you a brief introduction of all these four topics, and then tell you how this course will be organized, okay? And how is the evaluation will be done. Okay, so again, this nanophotonics studies the interaction between light and material at nanoscale. Okay, so if here I draw a bunch of optical or photonic applications depending on their scales, and you can see here the centimeter scale or millimeter scale photonic optical fiber and camera lenses, or this is macroscopic objects. And if you go down here, these are the applications of what is called microphotonics. And the sizes of these resonators is about like a few hundred microns, or sometimes even a millimeter. And then what we are interested in here is like around micrometers or submicron scale, where the size of these features becomes similar or even smaller than the wavelengths of light. Okay, so if the size of the feature becomes smaller than the wavelengths of light, everything is changing. So you will see what I mean by learning this course. And here, what I draw is just to give you some sense about the sizes. So like a 20 nanometers is about the size of a virus, and then 2 microns is about the size of some cell ingredient, and so on. So we are talking about like about 1 micron to under size scale, and how the light interact with matter at that scale. Okay, and again, if you have any question, please use chat room, or you can unmute yourself and then say anything. Like, feel free to interrupt. It'll be totally fine. And I actually prefer to be interrupted. Okay, so just ask any question if you have any question. Okay, so these are our topic. So first, let's briefly introduce what is photonic crystals. And photonic crystals, to understand the photonic crystals, it would be better to introduce this atomic lattice. Okay, so all materials, almost all solid materials, are composed of atoms, and these atoms forms lattice structure, right? This is this periodic lattice structure, and this is an example of graphene. So you have carbon atoms forming a hexagonal lattice, okay? And because these carbon atoms has formed a periodic structure, the electrons in each atom can hop, between the atoms, neighboring atoms, so they can interact. Okay, and because of this interaction, the electrons form what is called band structure in this right side figure. Okay, so here the x-axis is the momentum of an electron, and y-axis is the energy of an electronic state. So you can see it has a specific, electronic states follows specific energy momentum relation, and this is a key of understanding the electronic properties of solid materials. And similarly, what people did with photonics is that now we create periodic structure with two different materials. Okay, so in this 1D case, you have 1D periodic structure and 2D or 3D periodic structures. And because of these periodic structures, photonic structures can form a band structure like this. So just like electronic states form a electronic band structure in solid material, photonic structures can form a photonic band if you make a periodic material. And you can do lots of interesting things by using these type of periodic photonic structure. And here, the size of each layer is about a wavelength or even smaller than the wavelength, so that now we are in the scale of nanophotonics. Okay, so let me give you a simple examples of photonic crystals. Here, this is a natural example of photonic crystal. Everyone probably, not everyone, but many of you actually probably heard about this. So this is called a Morpho butterfly. And this butterfly has really beautiful, the wings of this butterfly has really beautiful color, this blue color. And this blue color, it turned out that this blue color is originated not from its material, but from its structure. So if you look at the cross-sectional profile of this blue colored regime, which is figure A here, it forms, this strange structure, and these structures forms a periodic, has periodicity in this vertical direction and lateral direction too. Okay, and this is a schematic image of this structure of a Morpho butterfly. And then if you actually run a simulations of by shining light from the top to the surface of a butterfly wing, you see here when lambda is 0.42 micron, which is blue light, most of the light is reflected. Okay, so light cannot penetrate inside the wing of a butterfly. But if you look at other color like 0.6, which is about it's not red, but it's about yellowish color. You see most of the light is just transmitted, and of course some is reflected, but reflection is not as strong. Okay, and because of this butterfly wings have blue color, because most of the blue color light is reflected, and all the other colors are kind of transmitted or absorbed. Okay, so this is a natural example of photonic crystal. So what's special about this is that if you let's imagine that you take this material, this black material, and then make it into a flat surface without any structure. Okay, then you may not be able to see any color. So what this tells you is that this blue color is originated from the structure itself, not from the material. Okay, So that's the kind of non-intuitive feature of nanophotonics. So if things become very small and organized, then your structure becomes really important. Not only the material, but also the structure becomes important. Here's another example. There are like a bunch of examples of natural photonic crystals. So this 1D photonic crystal is again the Morpho butterfly, and then here's how does it look like in SEM image, electron micrograph image. And here this is a feather of a peacock, and you see if you give a closer look, this feather actually is looks like a 2D photonic crystal, and then that's why this feather has really, you know, colorful color variations. And here, this bug, the surface of this bug also has very weird periodic photonic structure, and that's why it shows these weird colors. Again, this you know, bright, vivid color contrast is not due to the consisting material. It's due to the structure of material. And also, this is opal, which is a famous gemstone, and this opal tends to have this structure. If you look closer using SEM electron micrograph, okay? So it has periodic structure, as you can see, and because of this periodic structure, the opal shows this mysterious color variations depending on the angle. So any questions so far? Okay, well, again, if you have any question, you can interrupt anytime, or you can type in the chat room. You can always interrupt. Okay, so what's the applications of photonic crystals? Well, photonic crystals can be used in creating waveguides or like functional filters. So this is one example. So you probably see these punched holes forms a periodic structure. And because of this periodic structure, this part and unpunctured regime have different optical properties. And by using this optical property contrast, you can guide waves through this regime. Okay, so this works as a photonic waveguide. And now you change these holes, sizes of these holes, a little bit different from the holes in the background. I don't know whether you can actually notice this or not, but the sizes of these holes are actually a little bit different from the sizes of these holes. And because of that tiny size difference, now this area, the center area, acts as a photonic cavity. Okay, so light is trapped inside. So you can see here in the simulations, and cannot escape for a very long time. And so photonic crystals are famous for creating this cavity or optical cavities or optical waveguides. And you can actually using this cavity to create a laser. Okay, you probably learned, I'm not sure your background knowledge about the laser, but in order to create laser, you need high quality vector cavity. And photonic crystals, it's easy to create high Q factor cavity, and you can use it to create laser. And this has been published in Science 2004 from Yonghee Lee's group in physics department at KAIST. So this was his famous signature work. And another application is that, of course, these photonic crystals, the properties of photonic crystals depends a lot on the properties of holes and surrounding medium. If you drop a droplet of water and fill up the whole area, then you can basically change the color or optical properties of photonic crystals. And by using that, you can change the color of photonic crystal from here to from this to that. And this can be used for color changing paints or security paints or other applications. Okay, so Imunu actually asked the question. Thank you for asking the question. I really like this interaction. So Munu's question was that, can we use vertical pillar to form photonic crystal? I mean, replace holes with pillars. Of course, yes, you can do that. So instead of creating milling holes into a continuous medium, you can actually place pillars periodically to do the similar effect. And I'm not gonna go into details about how you can actually calculate the optical properties of photonic crystals. I'm gonna go through just 1D photonic crystal, but 2D and 3D, I'll give you some examples of pillar arrays. Okay, so another example is photonic crystal fiber. And this fiber, you probably know about this optical fiber. Optical fiber is used to transfer light information to very, very long distance, like kilometers or sometimes thousands of kilometers. And then if you drill the periodic holes in the cross-section of optical fiber, then you can actually change its properties dramatically so that you want to create, I mean, these photonic crystal fibers are used to do a non-linear optics, but I'm not gonna go into details right now. But anyway, this is one of the important photonic crystal applications. Okay, so now let's move on to the introduction of the plasmonics. So unlike conventional optics, plasmonics uses metals as their main ingredient. And the biggest difference between metals and dielectrics is that metals have free electrons, okay? And because of these free electrons, if you apply some electric field so that the nuclei of the metal, and the free electron cloud of the metal is displaced against each other, then they start to attract each other. And because of this attractive force, okay, well, this is supposed to be a video, but seems like it's not working. Anyway, this plasmon is a collective oscillation of free electron gas. And then at the interface between metal and dielectric, the photons, the electromagnetic waves, and these electrons of metal interact to form a surface wave. And this surface wave, if you look at the electric field of this surface wave, it's tightly confined at around the interface. And if you look at the dispersion relation of this surface plasmon, its momentum is always larger than the momentum of photon at the same energy. What does that mean? Is that the wavelengths of surface plasmon is always shorter than the wavelengths of light, which means plasmons are smaller than the photon. And because of this smallness, plasmons are useful in various applications, which I'm going to mention. Okay, so depending on its size, if you make metallic metals into a nanostructure, depending on its size, it starts to resonate at certain frequencies. So if you change the shape and the size of the nanoparticles, it resonates at different frequencies, and they have different color. Okay, although the ingredient material like gold and silver has its own color, if it becomes a nanoparticle, then depending on its size, it can have a like blue color or red color or green, any color you want, okay, depending on its size. So again, the optical properties of bulk material and nanoscale material can be very, very different, okay, depending on its structure. Okay, so here's an example of graphene, I'm sorry, just the plasmonics. So this is like ancient Roman artifact, which is called Lycurgus cup, okay? And what's special about this cup is that if you see the reflected light, so if you shine the light from the front and then just look at the reflected light, the cup looks green. And then now if you see the transmitted light, so shine the light from the backside and see the transmitted light, it looks red. Okay, so this is why it became a ancient Roman artifact. And then people didn't know why this is the case for like about like 1600 years. And very recently, 1990, people examined the material, this material, and this glass actually contains very, very small, here's a 50 nanometer, so very, very small metallic nanoparticles. And these metallic nanoparticles have distinctive transmission, absorption and scattering properties, and that's why you have different colors in different illumination schemes. So probably I'll explain about this in more detail when we cover the plasmonics. Okay, and this is another example. You see here, this is a stained glass, and all these beautiful colors are coming from, again, metallic nanoparticles in the glass. And depending on the size of a metallic nanoparticles, it has different colors, and that's how you actually create this beautiful color. And this is also about applications of plasmonics. So what's the applications then? What's the real application other than creating like beautiful things? Real applications are, because plasmonic nanostructures can trap light in a very small area, you can basically boost up the efficiency of a thin film solar cell. Okay, typically these thin film solar cells are so thin so that incident light are mostly just reflected or transmitted. You lose most of the light. Okay, but if you put a metallic nanoparticles in a thin film solar cell, these particles can hold light for a relatively long time in a very small area, so that it increases the chance to absorb. So that's how you increase the efficiency of solar cell using nanoparticles. And again, because plasmons are small, you can increase the sensitivity of molecular sensing, like even all the way up to single molecule level. Okay, and here this molecular sensing is done by what is called Raman spectrum, Raman measurement, and this Raman measurement or Raman process is second order nonlinear process. So its efficiency is proportional to the force power of the electric field amplitude. And because plasmonic particles or plasmonic structures can trap light in a very small area or very small volume, these efficiency of Raman process increases like by factor of a million or even larger. And you can also miniaturize all the photonic circuit components, because plasmons are smaller than the photons. And you can also create like what is called metamaterials, which is the next topic of the next slide. Okay, so now we move on to the metamaterials. So Greek word meta means beyond. So metamaterial can do like what the natural materials cannot do. Okay, so let's think about how the material is composed. Material is composed of atoms, right? And atoms have electron clouds, and these electron clouds and nuclei interact with incident electromagnetic wave, right? That's the feature. And what metamaterial does is you actually create a small object that can also interact with electromagnetic wave, but the size of the small object is so small, like much smaller than the wavelengths, so light cannot distinguish whether this material is composed of artificial material or natural material. Okay, so light, you probably heard about the term diffraction limit. Okay, so if two objects are closer than the half wavelengths, light cannot distinguish these two, right? So if you can create an artificial atom that is much smaller than the wavelengths of light, then in perspective of light, they don't know whether this material is composed of real material, real atom, or artificial atom. Although these two are actually, the size of these two are largely different. So that's metamaterials. And by using this idea, you can actually play around or engineer the effective permittivity or permeability by a lot. So you can create like all sorts of permittivity and permeability spectrum, and you can even create like negative refraction or hyperbolic dispersion relations, which will be covered in the lecture. Okay, so this is probably one of the first demonstration of metamaterial, and each of these, square is about 1 centimeter, and you may wonder how come this is then nanophotonics. Well, although this is 1 centimeter, their experiment was done in microwave frequencies. So for them, the wavelengths of an electromagnetic wave was larger than 10 centimeters. So this is much smaller than the wavelengths. So that this is still we can still call this as a nanophotonics. Okay, and by using this type of a structure, you can create magnetic permeability. You can engineer the magnetic permeability from positive to negative, which was never been possible with real natural materials. Okay, and you can also do the similar thing at visible frequencies by using much smaller structure. And you can see here, light is impinging on the structure with 30-degree incidence angle, but it's refracted with negative angle, unlike typical refraction, which is positive angle. So this is one of the important results in visible light metamaterials. And this is, of course, this is not a real image. This is just a computer graphics, but this tells you what's gonna happen if you can actually create negative index liquid. Okay, so this example, the image in the middle shows a straw in a typical liquid. So you see, because of the refraction, this straw looks deflected. And then if you do the same thing with negative index liquid, you will end up looking like something like this, which is really weird. And this is not just weird, but it has actual applications. So if you go next slide, if you have a negative refractive index, you can actually create cloak of invisibility. So this is again the experiment done in microwave frequencies. But what these two compares is that you have some cylinder here. And if you shine the light from the left side, what you're supposed to see is something like this. So here there's no field in the middle. So you immediately notice that there's something here, right? But now if you enclose this cylinder with metamaterial, with negative refractive index, now then what you can do, what this light does is that the light just circumvent this obstacle and then forms a unperturbed wavefront. Okay, so even though the observer, if you observe this light, you cannot realize that there was a cylinder here, right? So this is transparent in a sense. So this is a concept of cloak of invisibility, and this concept has been proposed by John Pendry, Sir John Pendry, in 2004 or something. Okay, 2004 or 5 or something. So at that time, this was really, really new. And people think that someday in future, we can actually create a, cloaking, visual cloaking of a aircraft, or we can do something like this. We can create like actual cloak of invisibility. Okay, but the biggest problem of these metamaterials is that it's really difficult to create because it's 3D. It's 3D, so you basically need to create nanoscale structure in 3D array, which is almost impossible. So people turn their eyes to some much easier topic, which is metasurfaces. Okay, now the idea itself is pretty similar. You want to create a meta atoms that has very weird optical properties, but now you place them into a surface, a form of a surface, rather than a 3D stacking. And that makes it the life much easier. So you can actually create many different devices. So here, what you can do is that you probably know about the Snell's law, which is the left-hand side of this equation. So n1 sine theta 1 is equal to n2 sine theta 2. That's the Snell's law. And then with the meta surface, the Snell's law should be changed with this additional term, because meta surface can give you additional abrupt phase gain or phase retardation, even with extremely thin layer, extremely thin thickness. So this shows the operation of one of the first metasurfaces developed by Professor Capasso at Harvard University. And you see here, you have a chevron type of a metallic structure, and depending on their angle, you can see the reflected light has different phase while they have the same amplitude, right? So even though this chevron itself is extremely thin, it gives a large variation of phase so that it can be used in many applications. So for instance, you can use it to create meta lens. Okay, so you can make an extremely thin lens that can be potentially replace the current thick, glass lenses. And you can also do a hologram, which is also very thin and really high resolution. And you can also do a optical modulation. So you can by using this extremely thin metasurface and using a electro-optic material, you can change the properties of metasurface in situ, so you can turn on and off the reflection from the metasurfaces. Okay, so there are a lot of interesting opportunities lies in front of these four applications.